Hello and welcome back to another episode with It's Dr. Dan, and today we're going to be looking at our exam number 2 review. So what this video is this is a recording from when me and my class in fall of 2024 went over our exam number 2, which is for both my Saturday and my Monday and Wednesday Chem 3A classes, so Introductory Chemistry. So the way that this review is going to work for everybody that is watching this, we are going to go through Canvas first and talk about all the different expectations of really what is on the exam. The thing I would recommend doing is utilizing all the different markers on the fast forward toolbar below to be able to figure out exactly which concepts that you want to go through. We will be doing a Kahoot review game. If you're interested in playing along, the link is in the bio in this video. You can use it. It is a solo game that you will be playing. I would recommend the way to kind of go about doing this review is watch the review portion of it at the very beginning, talking about what is on the test and what you're allowed to use. And then when you do the Kahoot, which is one of my old exams from a previous semester, you can play along with it. And then whenever you get a question wrong, you can fast forward it to that exact chapter marker that's inside of the video. Okay. So you can try to find that exact individual piece. So please stick along. It's going to be a little bit of a long video, but there's a lot of information that's packed on it. So I'm going to try to give you hints of all the little things that are on the exam that will really help you get a really good grade. So when you're kind of studying, this is a really good first benchmark. After that, I really recommend you kind of look at your notes, review them, then do the practice exam, which is on Canvas. And then afterwards, I would recommend practicing as many problems as you can, whether it's through practice problems that are found via your online textbook, or you can convert your homeworks into more practice problems, or you can do practice quizzes. More problems that you do, the better you will do on the exam. Okay, so best of luck studying, and I hope that this review helps, and I try to edit it down the best that I could to try to make it a little bit better and easier to follow along. All right, I will see you guys in the review session. So the biggest thing is just navigating our Canvas page. So going through the modules so that way you know where the exam study module is always the first thing. So if we minimize all this stuff that all of you guys probably have maximized, and half of you guys didn't realize you can do this. So I'm going to go to exam number 2, study module first. So as always, I put together a study module for you guys to kind of start off for kind of exactly what to study, what to review when you're kind of going through to prepare for this. If on the first exam, the score, let's say it wasn't really what you expected, or it was, I don't know, better than you expected, or whatever the situation is, especially because I'm speaking specifically to anyone that might not have had a score that they really wanted. If you were in that camp, then you really want to think about like, what did you do to try to really study? Because you probably want to change that up a little bit. So that way you don't repeat whatever might have happened. So like if you studied for an hour and you got like a 50, well, then clearly probably more time and more practice is kind of really needed. But if you studied for like 10 hours and got that score, then we got to really talk about what methods to really study. So the first thing I would do if it was me, and that's what we're going to do here, is obviously come to this because that's always a good start. But so let me tell you about what this exam is about, what's the format, and it's because it's going to be a little bit different than the last one. The big thing is I kind of made it so that way it was more favorable to award more points for you accomplishing, math. So the first thing is I want to say the first 18 questions are pure multiple choice, more on, I would say, concepts, theory, naming, swap drop formulas, maybe molar mass, like more basic type of calculations. So things that really, they don't award partial credit. It's only for just, like your intermolecular forces. Can you identify something as polar? Can you do, swap drop, things like that, and naming and those kinds of things. After that, the last 10 or so questions of the exam are all questions that I ask you to show your work for partial credit. So there's still multiple choice on most of them. There's a couple that don't have any multiple choice because it's something that you got to draw. So you might be able to guess, what could you possibly have to draw? What have you been drawing for the last 3 weeks? Or have you done a lab that maybe required you to draw something? So you might have to draw something. So with those ones, essentially, if you show your work and it's on the right direction, then you'll be rewarded partial credit for kind of essentially what you did when you were going through that specific thing. So, like, for example, if you were doing like a mole calculation of some type, whether it's like empirical formula, or percent composition, like those harder ones, and you were doing the right steps, but maybe you just forgot to do the end thing or maybe do some units, then you'll get partial credit for getting to that. Getting to the next question, because I saw one pop up. What are you allowed to use on this thing? So the things that you get, right, other than the partial credit thing, is that you get access to a note card, right? So a 3 by 5 inches note card, right? It's a normal note card. You can put whatever you want on it, right? You can use both sides. The only thing I will give you is I'll give you the yellow periodic table that and has and the whatever prefixes and stuff references on the back. So I'll give you the exact same one you got in the first one. If you want to put anything else on it, like VSEPR, like naming or notes, formulas, whatever, that's what you'd want to put on your note card. So you can put as much as that you can possibly pack on here. Biggest thing is that you got to be able to read it, right? So and know how to do it. Usually, the act of making the note card, like if you probably do that, like I don't know, tomorrow or something at some point, it kind of helps you study. So like when you're kind of maybe going through the review today, I would recommend writing down like any topics that you're like, oh crap, I better like really put this on my note card. Um, so in terms of the question on VSEPR, like how much of what exact geometries do you realistically need to know? I'll show you when we get to those questions. You don't need to know every single geometry because we only really went up to probably about row 4 realistically for 99% of the questions. So it's really those basic ones, being that those are the ones that are in biomolecules. So when you guys get into physiology and anatomy and start learning about proteins and um, enzymes and all these other like little molecules that you find within the cells, they're mainly just those first 4. You really don't see any of the other stuff in any other place. So if you need to know the VSEPR stuff, which you probably do, then I would recommend writing it down for yourself so you know it. You do get so the electronegativity values are actually on your yellow periodic table. A lot of people don't kind of realize that. So being that it's getting asked with the different sheets, right? What should you exactly really write down? Let's go through them real quick because it's not a bad thing to talk about in the handouts. So you'll get the yellow periodic table, right? That's the one thing that I said I'll give you. So with electronegativity values, they are on here, right? Which not everybody realizes. So just to point out to everybody, I pointed out into the Monday, Wednesday class, but Saturday I don't get to see you. So if you guys don't get that experience, but if you look at right at the bottom right of any of these different blocks, you'll see that that electronegativity value is right here at the bottom. So it's on all these elements. So it is there. It's just, I think even for me, I didn't even realize it was there until like my second or third semester teaching here, which is kind of sad. Because I didn't notice it was jammed there. I never seen it on a periodic table like that. So I was like, it's really nice. So it's already on there. So that way you know. And then it's on all the elements. So you got that there. So you have that. So with VSEPR, though, really you only need to know, I would say, the geometries in this top left corner. So just this area in purple. You don't need to know any of the ones below that. We never really saw any of them. So it's just six structures. It's not too bad um, compared to all of them. So if I'm going to give you a geometry, it's only one of the 6. If I'll double check the exam, if there is one that's not, then I'll give you make sure you have the VSEPR sheet, but it's only going to be in this top left corner. So I'll triple check. So only these ones. So not too bad. So if you want to put them on a note card, you can. I wouldn't blame you. It's probably a pretty easy one to fit somewhere on there for what they look like or how you want to figure out whether you want to put groups or lone pairs or however you've been doing that. Are there any questions about dispersion, dipole, and hydrogen bonding? If I may ask, what do you think? Do you think I would spend multiple days talking about it if it would be on there? And the answer is yeah, right. It is going to be on there. So not to be, a jerk about it, but it will be on there. So if those are things that you need to know those definitions, like for what they are, put that on there. But keep in mind, like this is more when it comes to using a note card, the way you want to make sure you use it is that you can find things, organize it well, and it's more of like a crutch. You don't want to use it as like your life support for the test, because if that is the only thing, like you never studied anything and that's the only thing you're using, it's going to explode so far in everybody's face. So use it as something that you're like, oh, I'm like not as good at remembering this thing, put that on there, like, so you have it. But usually I think like 90% of my students that end up doing note cards, you end up not needing it because you wrote it down, so you remember it. It's usually just a reference. So you'll get the yellow sheet, so you get all that stuff. So you'll have like your temperature formulas, which is probably like the one thing to kind of keep in mind. Like that's already on here. You'll already have, I think, so you have the value for how to convert joules to calories. So if you have to do that one, it's already on here. So for the thermochem stuff, and then yeah, so with your dispersion and all that stuff, then I would recommend making sure you're kind of semi-familiar with how to identify them. And we'll talk about how to do them when we're kind of going through questions. And then the green sheet, so the only ions that you need to know, so I checked, is the oxy anions. So these are the only ones. So if you remember the T43 method, right? So we've talked about that before. So I'm just highlighting the colors for the T43, then you will be okay, right? So those are the only ones that are on there, are these ones. Any other polyatomics that are on the exam, I tell you the name and I give you the formula. So I give you both, so that way you have it. Okay, so it's only these ones that these are the ones that I would recommend memorizing, because like I've said to Monday, Wednesday a couple times now, is that if you don't know them by the time you do chemical reactions, or when you're doing chemical reactions, which Saturday you started doing chemical reactions too, then it's going to make it 10 times harder to be able to balance these formulas easily, because you're kind of jumbling through 30 reference sheets when you're going through them. So put them on note cards if you haven't, just to kind of study them, right? So you already have to have one 3x5, so that means you probably have another 99 in the pack. So I would recommend putting them on flashcards or memorizing the T43 method, whichever helps. And if you don't know what I'm talking about, the T43 method, go to my video that's on it. Just go to it's in our Canvas modules for how to memorize it, or we can go over it later if need be too. That's fine too. But I didn't put any of these other modifier ones on there, so I made it not so bad. Canvas, right? So the big thing is here, right? So make sure you bring your Scantron. So you need the same Scantron as last time. So hopefully, I think last time I told everybody to buy, a couple, just so they had enough for the semester. So 95677 is the code for it. I'll make sure that there are extras in case anyone forgot it, but try not to make it a habit. If you did borrow one from me in the past, or then try to bring one back next time, pay it forward for another student. Other stuff that's here too. So I have the study guide here. There's a practice exam. I put flashcards up here as well too. So if you don't have time to make flashcards as study terms and things like that, then they're already here for you. So you can print them and cut them out, or just kind of review them if you'd like to. So you have that available. But from there, big thing to kind of point out is being that I'm going to get asked this by at least 5 people. This is not an actual assignment that you got to like turn in for exam number 2 study guide. It's just purely there. That's where your grade's going to go when you do the exam. Just so everybody hears that. It's just where I'm going to put the grade afterwards. So I know it says 100 points, but that's where your exam grade goes. Because with the study guide, I try to boil every chapter down to like the most important concepts. So I made this thing based off of our exam and then also like off my previous exams. So like things that might end up on the final exam. So it's like whether you need it for now or you need it for later. So that way you have it somewhere. When it comes to this test, the biggest thing for chapter 4, it really wasn't that much of it on the first exam. I try to actually not put that much on there just because for a lot of you, learning naming is honestly very overwhelming, right? It's a lot. That blue handout, right? That whole entire flow chart, like maybe you're starting to get it down and you kind of you're able to do it without looking at it. If you are, incredible. But it takes a long time to be able to develop that language of chemical formulas. So that's probably the biggest thing is there's going to be a lot of little naming questions and whether it's identifying like what kind of compound it is it ionic, is it covalent? Um, that's probably going to be the biggest thing is can you do things whether it's from a formula and make a name or go from a name to a formula. There's probably at least I would say 3 to 5 questions at least evolving around that. So you kind of like, that's a good chunk of points. Especially if you think there's only like 30 questions, that's 20% of the points could be from naming. So it's probably one of the bigger areas that had questions to it was with the naming stuff. Um, After that, when it comes to chapter 4, technically it's from chapter 4, but we didn't talk about it until chapter 7. But the phase changes are technically part of that chapter too. Make sure you know your phase changes, at least especially like so there's 6 phase changes. So make sure you're okay with like boiling, freezing, melting, condensation, sublimation, deposition, and I feel like I missed one. Is that all of them? Maybe it was all. Oh, maybe I said all of them. But all so you want to make sure you remember all 6 of them that are there. If you need practice, so you have a lot of options to practice problems. Realistically, for most people, reading your notes is never enough to get a good grade in Chem 3A or in physio or anatomy or microbiome. It's usually like the first step. It's like the first hour you go through your notes and you kind of figure out some of the things you need. But you realistically need to kind of practice as many problems as possible, which is reason why you have so much homework with so many problems. It's not to make you suffer. It's just because, as you can see, it really takes a lot of practice to kind of get an inkling of what's going on. And even then, you're like, we're still not even sure sometimes what's going on. It's a lot. Um, so you can either one of the things I have here is I have the recommended end of the chapter problems, so that go to our online textbook, right? If you didn't realize, right, we do have our online textbook on the right hand side, right, that you can click on at any point. So if the videos aren't clear, or if lecture isn't clear, or I'm not clear, try to read the individual chapter of the textbook. They're usually only like a couple pages for each section. It's usually a pretty quick read, and there's a lot of examples in it too that are ones that I didn't use in class or in lecture or in videos. So it's not a bad thing. Like reading sucks sometimes, but that's kind of honestly how I learned chem. My professor was amazing, but a lot of times not the best explainer of things. So you know, reading was what saved it. And there's a lot of examples that show you exactly how to do the problem. So I picked out problems that specifically are like ones that we either do in homework or that would be like on the test. After that, so chapter 5, big thing is with this one, mole conversions, right? We had 3 major mole conversions. You need to know how to do all 3, right? There's molar mass, so make sure you're comfortable with knowing how to go from grams to moles or moles to grams. Make sure you're okay with trying to set up those types of problems and how to find molar mass using your periodic table. Then after that is the mole to mole ratio, which is probably going to be the second most important conversion in the class because it uses the subscripts to go from one element to another, right? So if you had like something like, I don't know, C3H6, right, as a molecule, right, that means you have 3 moles of carbon, 6 moles of hydrogen, as like an example, right? And that's a ratio you can define. So that's really good. Avogadro's number, right? That's only for particles, molecules, things like that. We probably will never really see it again after this chapter because it's something that's used very sparingly because you don't really, we relate it to mass, right? We work in a physical world. Avogadro's number, we'll use it for now as a conversion to bridge the gap to theory, but we're mainly using mole conversions, the other ones, right? But you still got to be able to use it. So make sure you're okay with that. Probably the hardest thing that comes from this chapter is when we go over the review problems is doing empirical formulas and mass percents, which percents are kind of scary. They're kind of hard. I'm finding out that a lot of you really, really struggle with the idea of how to use a percent, just from, maybe gaps in like your math background. So practice percents as much as you can. There's going to be at least one problem that's a mass percent problem. Same thing with an empirical formula problem as well. So make sure you have some familiarity about it. You don't want to just use it as a toss away. Heck, you can even put like the step by step on how to solve them on your note card if you want. There's no limit to what you can put on it. So if you want to have a little procedure for yourself for how to do each type of problem, that's an option that you can do. So it just kind of depends on how have you been kind of working through all your homework and videos and all that stuff, right? You have choices. So that's what I did whenever I got a note card. I would just put like the step by step on it outside of the references. And you can fit a lot on these things too. And the other thing is too, a lot of people never think about is you can type this up too. You can actually set up a Word document to be 3 by 5 inches when you type it, and you can change the font size. So if it's better for you to type, which I know some of you submit your notes that are typed already, hint, hint, for those of you that do that, you could easily copy and paste things to your note card. So in Google Docs or on Word, you can do that. And if anyone's like, how the hell do you do it? I will gladly tell you if you just message me. Okay. So with Lewis structures and intermolecular forces, yes, your intermolecular forces. You need to be able to draw Lewis structures. There will be a few Lewis structure questions on the test, being that we had a lab on it, we had a homework on it. Luckily, MyOpenMath is not involved with it, so you don't have to struggle bus over if the dots are in the right box or did you put them back when you were done. That's not a thing. It's just drawing them out yourself. So either know your valence electrons or know how to the bonding trends, one or the other. Whatever method works for you, you will have to go through that process of trying to draw it. So I would really recommend just practicing as much as you can, so that way there's at least, I want to say, 4 Lewis structures, I think, on there, and a couple more on the fill in the blank area. Um, and then withdrawing them, can you label them as polar or non-polar, right? And then that would lead to intermolecular forces too, right? It's all related, which is that's when you use your electronegativity values. So if you need a little step-by-step on how to do that on your note card, that's something you can write out. Let's see. I didn't really put a lot of the prediction stuff on there. Being that with Monday and Wednesday, I didn't really talk about it with them that much. I just made them watch one of the videos on it, and same even Saturday, being that's what you do is watch videos all day for it. There's not really, I don't know if there's any predictions. The only thing I might have said is like which one's like the strongest force that might be possible type of question. Like, so if you have a molecule, like what is the strongest force? I don't think I had, if there is any comparisons, it might be off like dispersion. So like remember dispersion was the bigger the molecule, the more dispersion. So that polarizability. or if there's like a list of molecules, maybe ranking them in order for strength, which means like you could label like what's hydrogen bonding. Like, you're looking for those, you remember FNO, right? You're looking for fluorine, nitrogen, oxygen connected to a hydrogen. So like things like that when you're going through them. And if you want to practice them, once again, I do have a bunch of practice problems. Uh, Thermo, I actually kind of brought Thermo back a hair just because it's a lot of math. It's a little overwhelming, and I don't know. It's kind of, we really honestly don't use it a ton outside of chapter 7. You might see it a little bit here and there when it comes to the specific heat conversions. But when trying to think about what do you need the most to prepare, most of you want to do nursing or biology as a major, what do you need most moving forward? And honestly, I don't see how thermochemistry is one of those things. So I'm trying to think of, really, it's like looking at asking all my students that have ever taken that still talk to me too much from previous semesters. I'm like, what do you need for physio? So I'm trying to mainly focus on those things because I don't want you struggling in physio because it's such an overwhelming course. They all say it's harder in Chem 3A, which is shocking to me because I make this a lot of work. Um, so it's you kind of got to make sure you're okay with all that chem knowledge and bio knowledge before getting there, right? There's a reason why it's a prereq to prepare you for it. But the big thing is make sure you're okay with doing the temperature conversions and then just the specific heat calculations. So like any variation of specific heat, whether it's just using the MCAT equation, solving maybe for temperature, solving for specific heat, solving for mass, using that MCAT equation. That's really the big thing. Maybe it might be solving for final or initial temperature, right? In class and in the lecture videos, we had to rearrange the formula. You might have to be okay with doing that, right? Because you need to be okay with algebra. Um, so that's really probably the only thing other than just phase changes, labeling a phase change. But I did not put any of the delta H fusion or any of the delta H vaporization problems on there. And there is no heating cooling curve problem with multiple pieces on it. So there's going to be no like Q1 plus Q2 plus Q3, equals Q total energy. There's going to be none of those. They're a little too hard for this, but they could be on the team assessment though. So being that after the exam you will have the team assessment, but you get to struggle bus with your partner. So and you have your notes for that. So it's a little different if it's on there. I'm still making it, so I haven't decided what's on there yet. Okay, so that's that, right, with the module. Are there any like questions about like any of that stuff so far? I know it's a lot of just me talking and kind of hand waving at the moment, but um, it's kind of my thoughts with the exam and just trying to give you hints of what's really on it in terms of how to study, right? So obviously, you got to ask yourself what you did last time because maybe it worked, maybe it didn't. If it did not work, the thing I would do if it was me is I would read my notes first just to kind of refresh my brain of everything you've been really talking about over the last 4 weeks. And it really wouldn't hurt of just kind of skimming through your chapter 1 through 3 notes as well, because a lot of those skills you're probably using still, especially sig figs, percents, math in general, and maybe even atoms and ions. Like if any of that stuff is a struggle, review it, kind of just look through it, skim through it, just so that you're like seeing it again. It kind of helps. That's step 1. After that, what I would recommend kind of doing is I would say it might be better to take their time and really probably go through the practice exam would probably be one of the first things. So I do have a practice exam on Canvas that you have available. So you can go through that one. That one is an old exam. So that one is from fall of 2023. So it's from last year. It's a little bit harder than yours is, a little bit. There's a lot more. There's like delta H fusion, vaporization stuff on there, and some prediction stuff for intermolecular forces, which I didn't put on our exam just because like the students then struggled with it. And I'm like, I feel like I see the trend every semester. So I'm like, why make it harder on you? There's no point. So that I'm not gonna that one's you don't have to really worry about too much if you're not able to get it, but it might be on the team assessment. So if you want to know how to do it, it's not bad practice. Um, After that, obviously you want to finish all your homework assignments as soon as possible. If you're still like watching videos and finishing homeworks the day before the test, it's kind of spelling out a recipe for disaster. So I would recommend trying to finish as much of it as possible at least 2 days before. So that way you're not just spending all this time just trying to get done the fundamentals. You want to be able to review things and absorb information versus just kind of like I don't know, only focusing on one thing, right? That's kind of one of the downfalls for a lot of you. It's really easy to fall behind in this class. You miss a day and then it feels like you missed a month. It's one of those courses just because we do so much every single week. So I personally would recommend trying to either you could rewatch videos if you want. It just depends on like how well do you remember the questions. If you want to redo them, that you could do that. But if you kind of remember them, there's no point in doing it again. It's more about fresh new problems. So the one thing that a lot of people don't realize is that you can actually convert your old homeworks to practice homeworks. So if let's see if I can find one of them just as an example. So let's say I kind of bring up this old one. So I have week three's homework. This one's not on the test, right? Looking at it. But as you can see, like I'm in a student view, so like I could redeem 5 late passes to open it back up, or I can click practice. So the thing is, what does practice do when you click that? Is it opens up a blank homework. It locks the assignment, so keep that in mind. So if you're not done it, do not click it. So if you're finished, if you click it, you're already done. It's already graded anyway. So it gives you a brand new homework and doesn't affect your grade. You can just do whatever problems you want to practice. You don't have to complete all 30 of them. You could just do like a couple of them just to see, hey, do you know it? And if you want, you can always ask for similar questions. So keep in mind, a lot of them shuffle through new numbers, new problems. So it's a thing that not a lot of people realize is like the practice button. It can give you new problems. So if you're ever like, oh, I wish he gave us more problems, I'm like, you got them. Here you go. Your wish is my command. So that's one thing. The other thing that a lot of people don't realize, so this one is Monday, Wednesday class, so it looks a little bit different than Saturday as a disclaimer, is that at the end of a lot of the modules, I'm trying to find one, is that there's practice quizzes that are available too. So, for example, at the end of chapter 6, for molecular shape, I have a quiz that you can take that pulls, I think, 10 questions at a time from a completely different bank of questions that none of you have even probably have seen yet. So it's like another 80 to 100 questions. So you can just try 10 of them, see how you do. So if you really struggling with moles, naming, and forces, then this is a really good one. It's multiple choice, which is what your exam's going to be. It's going to be multiple choice, so that way you can practice that. I think I have quizzes up to I want to say quiz number 6. I think, maybe 5 is the last one. So I think it's practice 5 and 4. I think for this one. So there's a couple of them. After that, you have the textbook problems available too. So that's probably anywhere from 200 to 500 problems. So for anyone that's like an A++ overachiever, that's like I want more, you got it. And for anyone that's like I just want to pass, well, you still need to practice problems, right? You got it too. So focus on what you don't know, right? So when you're doing the practice exam, write down whenever there's a problem that you feel like you had to like look it up, you had to look through your notes, you feel like you didn't get, because those are the concepts that either you want to write down on your note card for how to do it, or you need to study it and do more problems with it. One of the things I'm kind of starting to realize, which is kind of the curse of MyOpenMath, it's a blessing and a curse, that program. It's great because it tells you if you're right if you do, the problem correctly. That's fantastic. You get instant feedback. It's faster than I could ever grade. But the curse is that, if you get the checkbox and you're like, oh, I got it right, you got to ask yourself, do you understand the problem? Okay. Do you really get it? Because, if you're like, oh, I must get it because I got it right, that's probably does not mean you got it. You probably should try another one and just to really make sure that you're able to do it. So if you kind of see yourself doing that a lot on the practice test, that means you need to review it. You need to understand it, not just be able to regurgitate. You can't just memorize your way through chem. It's not like bio. It's not just memorize this textbook. You can't do that through chem, unfortunately. I wish you could. I wish that was the answer, but it's sadly not. It's too much math to do it that way. Yeah, and then one thing too is the Kahoot that we'll go through. It is an old test too. It is my exam from spring of last semester, so spring 24. So it's my most recent test. Well, almost my most recent. I guess I taught a summer class, but so this one's a pretty recent one. So I converted it to a Kahoot so that way you guys can see kind of what I had in mind back then. It's pretty similar to the difficulty of yours. There was a few things I might have tweaked here and there when I was kind of typing them in. I'm like, oh, I asked this one. Huh, okay, weird. So if there are another questions, we can go through that. So we'll go as long as like people kind of have questions, need help, as you kind of see it. So let me kind of bring that up, and then you guys can join it. So and okay. So and you guys can use your reference sheets, but kind of one thing I would recommend is when you're going through any of these, try to if there's something you don't know, just write down the topic for yourself so you know what to study. Cool. All right, so almost everybody got this one right. So with this one, the whole thing with this kind of question, sorry about that, is doing your swap drop, right, is the entire idea here. So remembering your charges is key, right? You're going to have a blank new periodic table. So if you need to write down charges, I kind of hope by this point you don't have to, but for aluminum, you might need to just because it's part of the steps, right? So if I were to just kind of real quick, just all right, so for the first problem, what we're going to be quickly doing is swap dropping. So the thing that's so common that students can forget is that when we're looking at aluminum, right? So this one is in the +3 column. So this is the first value in our steps when it comes to our cations. So it has a predictable charge. So we have aluminum, then we have zinc, right? And then our next step is silver. So what this is going to be is +3, +2, and +1. So 1, 2, 3. And then oxygen, right? So when we're looking at these, right, nitrogen is -3, oxygen is -2, and then fluorine is -1. So all we're simply going to do is we're going to take our aluminum, right? So it'd be aluminum 3 plus, and then we're going to then have oxygen 2 minus, and we're going to trade the numbers. So the 2 is going to come down to aluminum, and then the 3 is going to come next to oxygen. So what are we going to end up having? So we'll rewrite it. And we have aluminum 2 and then oxygen 3 for our next one, right? So we see that those subscripts are being traded, and as a result, it balances the ionic charge of our formula. So this is our swap drop, right? So this is something you need to make sure that you remember for this exam and for when we balance chemical reactions. Okay, so if you do get a problem like this, so I'm not going to tell the answer, but if you do get one, I would highly recommend you draw it. Unless you're really good at knowing bond trends. If you're not, then draw it so that way you make sure you get the correct answer. You don't want to just kind of pick the one that looks right. Like that's a recipe for disaster. And there's probably some people will try to do that. And if you are running out of time, great strategy. But if you have like an hour, then make sure you go through it. And okay, oh, wonderful. Everybody got it. Oh, that's fantastic. I love it. So with this one, right, just kind of showing it, really, if you know bonding trends, it makes this problem really easy. Carbon makes 4 bonds, right? So what does that really mean is that, well, it needs to somehow satisfy that requirement. So it needs the 2 double bonds to make that possible. And sulfur needs 2 bonds, so it fits really, really well in that situation, right? Because it can do that. All right, so double points. All right, according to the VSEPR model, the molecular geometry of the carbonate ion would be what? This one's kind of a hard one. You might have had the misfortune of having to do this problem on your homework. It was one of the extra credit ones, depending on which one you got. Either you got this one or you got nitrate. It was one or the other. Oh, speaking of which, there's going to be no resonance on the test, so don't worry about that. Okay, so drawing the carbonate ion is a very hard example. You might have had that misfortune of getting this assigned to you as a homework question, and it was an extra credit one, but it is very tough just because it has resonance to it and it has an ionic charge. So what do you do? So the first thing that we're going to do is we're going to write our carbon, being that's our central atom. It's the atom that can make the most friends. It can make 4 different bonds. So the first thing we're going to do is we're going to draw an oxygen on each side, and then we're going to assign its 6 electrons around it, and we're going to draw all 6 of them. Okay, so we're putting its 6 valence electrons around each one. And then what we will do is we're going to connect them with a single bond. So we're going to connect each carbon to oxygen. Now, in the process, you're going to see that none of these different elements are happy. Carbon only has 1 extra electron that it can bond to something. So what we'll do is we'll pick one of the oxygens to make a double bond. So, okay, we have that. Now, one thing about these is the oxygens are still not happy. They have this lone electron that's available to it. So what do we got to do? Well, you got to keep in mind that this original molecule at the very, very top, it had a 2 minus charge, which what does that mean? It means it has 2 extra electrons. It has so many extra that it's extra negative. So what we're going to end up doing is we're going to add those to the exterior atoms, the more electronegative elements that were missing to complete their octet. So as a result, you can see that if you look at one of these oxygens on the side, they now have a total of all 8 of its lone pair electrons. So it ends up being very, very happy with all of its valence electrons. So now the next part was, how do you assign the geometry? So what we do is we have our central atom here in the middle. And what we're going to end up doing is highlighting each of the groups that's around that central atom. So how many do we end up having? Well, we have 1, 2, 3 groups around our central atom, 3 groups, 0 lone pairs. So what we're going to end up doing is we're going to go back up to our VSEPR chart. So once we do that here, we're going to find our 3 groups with no lone pairs. So when we do that, right, we have 3 groups right here, no lone pairs. So where are we going to go is right here. So what does that tell you? You have a trigonal planar geometry for CO3 2 minus. And this structure does have 2 other resonance structures as well. It's something you might need to know for your final. I did not put it on this exam. It could be found also on the team assessment, which might be possible as well. All right, let's go on to the next problem. I'm like, what happened to the music? I'm like, okay. So with this one, right, you guys got it really quickly, so that's good. So hydrogen bonding, right, is kind of the big thing. So you're looking for a simple trend is what you're trying to find, right? So if you can find OH, or remember I said F, find F no, right, is the whole idea. So OH, NH, if you see OH, NH, or FH in a molecule that are next to each other in the formula, it can do hydrogen bonding. So with this one, right, with methanol, which is the one in yellow here, you see that it does have that that entire I don't know why this thing paused sharing. You have that OH signature that was on that particular one. Okay, let me stop sharing so that way it comes back up. I don't know why I paused it. Weird. Okay. but OH is kind of the idea here. So with hydrogen bonding, it has to follow that definition. Whereas the other ones, you're just looking for something electronegative for dipole-dipole. And then dispersion means it's nonpolar is really the thing that you're looking for with for our class. But keep in mind that all molecules can do dispersion. Even polar ones can. But it's the only thing that the nonpolar ones can do. Which one of the following is polar? And sometimes you have to draw them too. If you have to, go through and do it. It would make it a long problem, but it's better to do it correctly than to blindly guess type thing. There is a trick to this one, believe it or not. So let's kind of talk about it. So let me write down all of the, actually, I guess I will have it to the side. So one of the things is when we did these in class or in videos for Saturday, there was a couple little credentials that you kind of like would check off to figure out if something was, what do you call it? If it was nonpolar or not was the entire idea. So going to my tablet, the one thing is with this one is if you can see an atom has all the same elements all around it, then that means it's considered to be nonpolar, right? So what do I mean by that? Well, if I kind of draw these really quick, so if I have like CO2, for example, right, that one is evenly pulling from oxygens on both sides. The CBr4, even though CBr is very polar, but when you end up drawing it, you see that it's all the same element on all sides. Same thing with CH, same thing, same element, all sides. The only one, so even F, right? So that's a very polar atom, but remember, whenever it's the exact same element, they cancel each other out. So even if you say like, oh, 4.0, 4.0, they subtract and it makes a big 0. So the only one that has something different about it, which even if you're not quick, is you see that there's this one little atom. It takes the power of one atom to make the whole thing different. So CHBr in this case, so if I kind of maybe just change this one structure over here, and I put a little H, well, now it's all pulling in the direction downwards. So it's pulling towards the bromines. So that changes polarity. So if we were to look at this and think of reviewing, because, a couple of you asked about intermolecular forces, well, what forces can these do? So once they are nonpolar, they do dispersion. So you're going to see that all the ones that canceled all do dispersion, right? So all the ones that pretty much all of these guys all over here, right? All these will do dispersion. Whereas this one, the question is, well, does it do hydrogen bonding or not? That's your first criteria. If it can do hydrogen bonding, you know what it is, right? So remember F no. But if you see an electronegative difference or a very electronegative atom, then that's when it would do dipole-dipole. So in this case, we would have dipole-dipole. Right. That's a tough one. It's really tough for you if you didn't get it right. Don't worry. It's like, well, how we learn, right? I'd rather you make mistakes and learn from them. What is the predicted molecular geometry of the CH4 molecule according to the VSEPR model? So I just drew it. See if you can remember what the drawing was. Maybe you wrote it down for yourself. You guys are just too good. All right. So CH4, 4 groups, no lone pairs on it. So just like kind of for the video's sake, I know you guys got it right, but I think a lot of you guys do use this video. It's actually shocked how many people watched it for the last one. So let's just look at it just so we can kind of see. All right, so the big thing is when you're drawing this, right, you have the 4 groups. So even if you're not an expert at drawing VSEPR, that's fine. You can draw the Lewis structure. But you do need to know how to count groups. So we do have 1, we have 2, we have 3, we have 4. So we count bonds and lone pairs attached to the central atom. So just as a little reminder, right, this guy here is central. It's in the middle. That's what you're looking for. So all we're going to do is we're going to go down to 4 groups, and then we have 0 lone pairs. So what does that mean? Is that our molecule in this case is tetrahedral. All right. Helium atoms do not combine to form helium-2 molecules, yet helium atoms do attract one another weakly through which intermolecular force? This is when in class in the videos we talked about something called polarizability. And I kind of used a maybe not the best example of using coin flips to describe which side the electrons would be on. Okay, so with this one, how exactly can you look at it? So it's a noble gas. The noble gases, right, they have a complete octet. They're on the very right side of your periodic table. Sorry, I'm like pointing this way and it's going left of your screen. Right side of your periodic table. So being that it's on that far side, that means that it's something that it doesn't need electrons. So it doesn't bond typically with different elements. So it can still do dispersion because you remember if a molecule kind of bumps another molecule, what happens is the electron cloud kind of shifts as a result. So if you kind of think yourself slamming on your brakes, right? You are an electron in your car, you shift forward as a result of that forward momentum of your car, how much it had before the brakes were hit. So when that happens, it takes some time for you to kind of fix yourself up because you're like, oh God, heart's racing a little bit. Same thing with electrons. They just hit another atom. That's scary. So whenever it's something that's nonpolar or a noble gas or a diatomic gas, like let's say any of the 7 diatomics, they do dispersion. Okay. So dispersion is when we talk about nonpolar elements. Okay. Let's do the next. And like I said, if at any point you guys have questions about this intermolecular force stuff, that's like it's still not quite making sense. So which of the following is defined as an attractive force between polar molecules? So which one would be considered an attractive force between polar molecules? Is there a link to play this Kahoot? Yeah, there will be a link to put it in the modules. So it will be one thing I probably should have mentioned this earlier is like if you're not able to whether we get through this all, I don't know. Depends on how many people are here towards the end of it. But one thing that I was really recommending, because this, like I said, this was an old test, is so the Kahoot link will be in the YouTube bio for the video, and then it will also be in on Canvas as well. So you can kind of like play along, and let's say you don't get one right. I've been putting chapter markers in the video, so that way you can quickly find exactly which question you wanna review. Um, it might take me probably until the end of tomorrow to. I'm gonna edit tonight. I'll probably post it tomorrow, and then I'll probably put the chapter markers Thursday night, probably because editing a 2 to 3 hour recording is a nightmare. I found out last time, but I I did get it done, so I'll get it as fast as I can with whatever sleep I can get muster out of it. But yes, there will be a link. All right, so it looks like this one you guys are split, which actually that's okay because even for the people that picked yellow, you I believe were correct. So which was number 2. So with this one, it's kind of a trick question, sort of. So one of the things is when they're polar, you are all correct. It does dipole-dipole. No denying that. But you have to remember that every molecule does dispersion, right? Every single one of them. So, with that in mind, right, that's if like you had one where you had to list all the forces the molecule can do, its strongest is dipole-dipole. However, it can also do dispersion, right, as well. So that's something to kind of like keep in mind with this particular video. So going through every single piece of information. So dipole-dipole is the strongest, then dispersion. In order for it to do ion dipole interactions, it would have to be solvating something. So you know how in lab, so Monday, Wednesday, when we had lab this week, we did the chemical reactions lab and we used the solubility tables. Those are talking about ions being formed, and that's due to water making an ion dipole interaction and solving and ripping apart ionic bonds like phone books. Which of the following molecules is non-polar? So another one about polarity. I put a lot more intermolecular. I put some extra intermolecular force questions in this just because a lot of you have been messaging me about them. So the trick with these is typically geometry is one, right? So if you have like the same element all around the molecule, then it's a good chance that it's nonpolar. However, you have to check, does the central atom, does it have lone pairs? If it does have lone pairs, then that means it's polar, right? So for Chem 3A, that definition works pretty well, right? And even if any of you go to tutoring, drop-in tutoring, I've been hearing a lot of the drop-in tutors have been saying that too. It's true about like 95% of the time that you can go off the lone pairs off the central atom. There are we've done examples in class where that's not true, but make sure you do check the electronegativity too for lone pairs. You can quickly look up the values. Like pH 3, it looks like it should be polar, but it's not. Okay. So this one was like across the board. Everybody pick something. See what we got. All right. So CO2, we drew that one before. All right. So that one was a linear molecule when we were looking at that. So if I quickly kind of share my tablet just so we can kind of talk about it. So that one, right, was a linear molecule. So we had it up here on the top left. So we also have NH3. So if you kind of remember, nitrogen has 5 valence electrons to it. So that means it's going to have a lone pair on that central atom. Even though it's bonding to the 3 hydrogens on each side, you can see that it has 1 lone pair. So you can take that one out. That one's polar. CH3Cl, you can take that one out because that has 1 atom that's different, and it's chlorine, which is very polar. Water, hopefully water's polar, right? It can do hydrogen bonding. So if it can do hydrogen bonding, very, very polar. So you can rule that one out. OF2 is actually very similar to water. So once again, you got the 2 lone pairs on oxygen, and then you have the fluorines on each side. So that one's slightly polar too. So that's kind of all the molecules there. So the only one is CO2. Okay. The total number of lone pairs in NCl3 is what? So with this one, you have to draw the Lewis structure and then make sure you put all your lone pairs, and you want to count every pair. And if you think you can do it without drawing it, then super impressive. That means you're very well practiced and you know how to do it, which maybe some of you do. That's possible. So good job. So it looks like most of you guys got this one right. So, with this one, right, the first thing you want to draw is nitrogen. It's your central atom because it can make the most friends. It can make 3 bonds, whereas chlorine can only make 1 bond. So what we're going to do is we're going to draw chlorines on all sides. So with its 7 valence electrons. And where we got 7 was from the row of the periodic table, right? So keep that in mind too. So if you want to, I can show you guys that just to review the valence electrons. So we're going to draw the structure. We're going to connect it all together. And now we're going to count how many lone pairs. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 pairs. Oh, I don't want to write that in highlight, but 10 pairs that are here. All right. So when it comes to the valence electrons, let's kind of quickly review that. It's actually, there's a quick little trend to kind of how to do this. So the thing I kind of mentioned to everybody in class for Monday, Wednesday is you can simply just kind of ignore the ones for each of the periodic tables. So right now I'm kind of writing over the ones on the periodic table. So if you ignore the tens position, this is how many valence electrons there are for each individual column that's here on the periodic table. So you have 3, 4, 5, 7, and 8, and you can do the same thing on the other side, but it's already 1, 2. So it's 1, 2, 3, 4, 5, 6, 7, 8. So we can kind of bring that back to normal. But that's kind of a quick way of really seeing it without having to do too much work. All right, so predict the molecular geometry and polarity of the SO2 molecule. This one's kind of a hard one. just because it violates the octet rule. Okay, so let's see. We were kind of split between linear and bent, and looks like everybody, I think it looks like everybody for the most part got polar, which is good. So let's kind of take a look at this one, just because this is a trickier one. I don't think I put any octet rule violators on the exam, but could be wrong. I'm trying to recall. I don't remember. I think I tried to stick to just regular structures. So nothing that's like too complicated with this particular one. So if we are to look at this one, the first thing we do is as write out sulfur. So sulfur typically can only make 2 bonds. The thing is, it does have access to be able to expand its octet, being that it's on the 3rd row of the periodic table. So if you have 3rd row or below, that means it can violate the octet rule. So, which is kind of important to remember. So it's just row 3 and below. So if we put in oxygen, right? The big thing is you can see that it won't be happy just with doing a single bond. It's going to have a lonely electron that is going to connect to nothing on the back side of it. So if we kind of like see here, we have this electron that's just near nothing. So what are we going to do with this thing that's over here? Well, we are going to end up moving it so that way it's going to become a double bond. So if I do that, we're going to end up splitting the sulfur lone pair on both sides. So that way it can make 2 extra bonds with oxygen on both sides. So we're going to move these lonely electrons and therefore making double bonds. So this is violating the octet rule. You'll see that it actually has 10 electrons being shared around it. So you got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Ooh, gross. So it's a lot. So if we were to then look at how many groups are there, well, there's one on the left, one on the right, right? And then you have the lone pair on top. So with this one, you have 3 groups, 1 lone pair. So what are we going to do is we're going to go to our handy dandy chart somewhere. So we have 3 and 1. So where's that going to end up falling? It's going to be right here where we have 3 and 1. So we're going on both sides to be able to see that it's bent. And being that it has that lone pair on the middle of it, it's going to be polar. And you can go off the electronegativity too to figure out that's polar too if you want. That's a tough one. I think that one's a little harder than kind of what I have in mind for the current one. But, I'll say one thing is not hard, and then doing the practice stuff, doing the practice exam multiple times, it probably is only, oh, I should try to make that bigger if I can. It probably is only so useful to an extent. I don't know, hopefully me zooming in on that helps, but so you guys can see that a little bit better. You should be able to see the choices on your phone or on your computer, hopefully. Question was, which of these Lewis structures is incorrect? So which one is wrong? Is the question. So which one of these is wrong? And usually you're looking for 2 things with wrong Lewis structures. You're looking for octet rule violations, meaning too many electrons or too few electrons. So that'd be the first thing. After that is, do you see any things that aren't following bond trends? Would be the next thing. So if you see like oxygen is making 3 bonds in this case, like, is that possible? Well, it totally depends on this charge up here. Does that allow that to happen? It might. You have to kind of draw it out and take a look. Or like nitrogen up at the top, right? It has NH3. Nitrogen can make 3 bonds. So, okay, that one looks pretty normal for D then. NH3 we've drawn already tonight. Same thing with C with CH4. We looked at that one too. Same thing with B, right? B as well is also pretty normal. So looking at that, really the unnormal ones are the A and E, which I could understand you guys picking those ones. So E is hydronium. So hydronium is actually, we're going to talk about that when we get to acids and bases. It's actually one of your polyatomics. If you look at the very bottom of the polyatomic sheet, H3O plus, that is the structure for it. So it actually, oxygen loses 1 electron, which is why it has the positive charge. So you see there's only 5 electrons around oxygen that started with. So that's showing you it's 1 less. With A, with nitrogen, nitrogen wants to make a triple bond. So with that one, it ends up having actually don't think it has. It might have too many electrons to start with because 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, so it has 12 electrons as well. N2 only has 10 electrons. So there's actually too many electrons for A as well. So if you count all the dots, you'll actually see that there's how many atoms are in 7.12 moles of gold. Ooh, finally on math, our favorite. So with this one, the first thing you want to do is you want to write what the given term is. And you got to think about, well, what's the conversions that you have available for moles. So it's asking you to figure out how many atoms there are. So that's telling you it wants something that's really tiny, right? That's the entire idea with anything with moles. So when we do molar conversions, we have a few options. We have molar mass, which goes between grams and moles. We have the mole to mole ratio. Okay, so which goes from like moles of A to moles of B, right? So whatever those two things are. And then the last one is Avogadro's number, which is from moles to particles. Or when we say particles, that could be all kinds of tiny things. It could be atoms, it could be molecules, formula units, whatever, anything tiny, whatever you can wrap your head around that's really small, we could use it. So in this case, we're going to use Avogadro's number. So it's 1 mole is the equivalent of 6.022 times 10 to the 23 atoms of gold. So when we do that, right, we can see moles of AU cancels. And then as a result, when you do this problem, you're going to get 4.29 times 10 to the 24 atoms of gold. So you just multiply across. This is the entire idea of what we're going to do here. So it's one of those like kind of more basic conversions. So definitely make sure you practice your mole conversions. There's at least, I would say at least 4 to 6 of them on there. There's quite a bit of them. The exam's pretty evenly split between everything, but those ones are probably one of the more important things to kind of master for later in the semester. Calculate the molar mass of tetraphosphorus decoxide, and then give you the formula. And it's a substance that can be used as a drying agent. So how would you calculate the molar mass? So how to do this one, right? Is just using your periodic table, looking up all the different values on it. So what we need to do is we need to find phosphorus, we need to find oxygen. So we can find them in the nonmetals over on the right-hand side. So here's one, and then the other one, oxygen, is up here. So all we're going to do is being that we had P4 O10, we're going to take 30.97. We're going to times that by 4, being that was your original formula. And then you're going to then add it to 10 oxygens times 15.999. Okay. Now, when you end up doing that, what you're going to get for your final answer, so being that's talking about for molar mass, you should have 283.88 grams per mole should be our final unit. I realize that those were showing in AMU, so we should have been showing those in grams per mole. Came to that problem. Okay, so that would be how to do that problem. For the last problem, where did I get the 6.022? So that's just Avogadro's number. So that's just the constant. So you can say you have 6.022 times 10 to the 23 of anything you want, and that's equivalent to 1 mole. So you can do that for any of your Avogadros number conversions. So it's always 6.022 times 10 to the 23, whatever thing it is, right, is equivalent to 1 mole of that thing, whatever it is. Okay? Just, we'll just say it's the blue box. 6.022 times 10 to the 23 blue boxes is equal to 1 mole of blue box. And it's whatever you need it to be. It's a simplification. Which of the following is the empirical formula for hexane? So, and I give you the formula, C6H14. So what is the empirical formula? Okay. Oh, good. Everybody knows how to find an empirical formula. So with this one, right, it's just the simplest ratio. So you're just trying to figure out what can you divide them all by the same number. So in this case, you can divide them all by 2 in this case. So C3H7, you're looking for whatever the least common multiple is in order to divide it. Household sugar, sucrose, has a molecular formula of C12H22O11. What is the percent of carbon in sucrose by mass? So what is the percent of carbon in sucrose? Oh, good job to those you guys that got it. This one's actually a pretty tough one, to be honest. I think it's a long one, just because it involves a lot of looking up your molar masses and all that kind of stuff. So how do we kind of do it, just in case you weren't sure how to do it or maybe just kind of guessed? So we're trying to figure out what the percent of carbon is in this molecule. So the whole idea is, when we think of percents, is that it's defining what is the part all over the whole. So, well, in this case, what is the part? Well, the part is carbon 12, because there's 12 carbons in this molecule, and it's all over C12H22O11, which is your whole, right? So then you're just going to times that by 100%. So what we need to do is we need to look up the values for carbon 12 using your periodic table, right? Or sorry, for 12 carbons. So all we're going to simply do is just take 12.011 grams per mole. So that's coming from the periodic table. We're going to times that by 12. I'm just taking it from, where's carbon? Up in number 6. I'm just taking it from right here. And what we're going to do is we're going to divide that all by the molar mass of sucrose. So with this one, right, it's 12.011 grams per mole times 12. And we're going to add that to hydrogen, which is 1.008 grams per mole times 22. And we'll add that to oxygen, which is 11 times 15.999 grams per mole. So we're grabbing all those from our table, right? So every single one of these is on the periodic table. So when we do that, what we're going to end up getting for our problem is we'll have a pretty big calculation to kind of plug in. So you're welcome to try to, do one piece at a time, right? Solve what's on top, put it on bottom, right? But in the end, what you will get is that there'll be about 42.1% of carbon when you divide these two massive numbers by each other. Okay, is the whole idea, right? So you multiply everything on top, and then you want to multiply all the stuff on the bottom, and then divide the two numbers by each other. All right, which of the following is an empirical formula of a compound that is 52.15% carbon, 13.3% hydrogen, and 34.73% oxygen? With this kind of problem, it might not be a bad idea to maybe have like the steps probably available to you on your note card, just because it's arguably the longest problem that you could have on this test, I think. And at least I think it would be. Maybe Thermochem you could argue is longer, but I don't know. They're hard. They're really hard problems. All right. So the first thing that you got to do is you got to set up the problem. So every percent, the way that you can actually write it is you can write it as grams. So now the way that you can reason that you can do that is that we're making an assumption that you have that many grams of each element in 100-gram sample, right? So when you kind of add all these up, it equals to, it's out of 100. is the whole idea for it, being that it is a percent. So we're making an assumption. We're trying to figure out how much of each mole is inside of this. So we convert it to moles, being that's the common unit between all elements, all substances. So how do we go from grams to moles? Well, that's going to be using one of our different conversion factors, right? So we had earlier, we can use molar mass, mole to mole, or Avogadros. So in this case, we're going to end up using molar mass, which is our common factor here. So we're going to once again use the values from our periodic table for molar mass. So we see that 1 mole of carbon is equivalent to 12.011 grams of carbon from your periodic table. Then we have 1.008 grams of carbon is equivalent to 1 mole of hydrogen. And then we can also write the one for oxygen 2. Now, when we solve for that, we'll do the first one. So it's 52.15 divided by 12.011. So you should get 4.34 moles of carbon. Then for the next one, we would do the same kind of idea. So we're going to take 13.13 and we're going to divide that by 1.008. And we'll get about 13.0 3 moles. I'm just kind of rounding it just to make it a little easier for me to write down. Then the next one is 34.17 divided by 15.999. And we should get 2.17 moles. Now, the thing with all these is that these do represent subscripts, but we can't have a half or a percent or a decimal of an atom. So what are we going to do is we're going to divide them all by the smallest moles that's available. Okay. So we're going to divide all of them. So we're going to divide until small is the way that we like to phrase this. So we'll take our individual species, right? So oxygen was 1, right? So it's 2.17 divided by 2.17. Then for carbon, it's 4.34 divided by 2.17. So that would be 2. And then for hydrogen, when we do 13.03 divided by 2.17, we'll get roughly about 6. So our empirical formula for this molecule is going to end up being C2H6O. And that's how you do an empirical formula. So the first thing is convert to moles, then divide until small, and then you multiply until whole if needed, right? So we didn't have to multiply though in this case. So it's just like what you did in experiment 5 and what you did in the empirical formula videos. That's probably the hardest mole problem that you could have, something like that. You have 5 vials, each contain 12 grams of a solid metal sample. Which vial has the most metal atoms? So you have calcium, platinum, barium, gold, and silver. Which one would have the most atoms inside of the vial? They each contain 12 grams of that substance. When you realize the trick, you'll see that it's actually not so bad. So with this one, how do you do it is really the question, right? You might be having. It's a lot easier than you might actually realize. So the thing that can compare all these species is moles. So you can kind of go about it 2 ways. You could convert everything to moles if you want to using molar mass, because you know that each of them weighs 12 grams. But that's kind of like a little too much. Really, all you need to do is compare the biggest one and the smallest one. So what I did here is I just boxed off where the 5 were on the table, right? So it'd be between calcium and gold. Well, which one of them has more moles? Because you would convert it with Avogadro's number, right? So if you did calcium, right, if you had 12 grams of calcium, you would convert that using its molar mass. And you're actually going to see that it's a bigger ratio. It's going to be a bigger decimal value that's here. So if we take 12 divided by 40.08, it's going to be about 0.299 moles of calcium. Whereas if I do gold, Well, that's going to be a lot smaller of a number. You take 12 grams of gold, divide that by its molar mass, which is 196.97 grams, and convert that to moles, and you're going to see that it's going to be a lot smaller of a number. It ends up being 0.0609. Okay. So why do we care about this when it asks about atoms? Well, you would take moles and you multiply it by Avogadro's number. The one that would end up being the bigger number is the one that's going to have more atoms in your problem. So it's going to be calcium in this case, is going to end up having more atoms to it. And if you need to, you can multiply it by Avogadro's number to prove it to yourself. But whatever has more moles is going to have more atoms. Okay. So you can kind of do it without doing a ton of math if you want to. You could also see which one is the smaller molar mass too, if you're able to do it that way, but only if you really, really understand it really, really well. Let's try this next one. Which state of matter is described as having a definite shape and volume? So what has a definite shape and a definite volume? Theory questions, right? This is the bread and butter. Get these right. These are the ones you want to get right. Don't overthink it, right? Solid, it has the same shape no matter what. It's going to have the same volume. So a lot easier, a little bit easier of a problem, right? No math. And there is a decent number of questions on this one that are not math, so which is kind of nice. Being that we did have a lot of theory stuff, so make sure you're reviewing it. If you need to put it on flashcards, you can. You can use your note card, whatever you need to do. What is the phase change from a solid to a gas? So how do you go from a solid to a gas? All right, so air moves between either sublimation or condensation. So a lot of those all have to do with the gas part of it. So solid to a gas was one of the weird ones. That's when if you take something that's solid, immediately goes to the gas, so it just immediately evaporates. This is sublimation, is what that was called. To go backwards, that would be deposition. Condensation for the person that chose purple. That's going from a gas to a liquid. So that would be like when you have dew on like your windshield in the morning or on the grass outside. Place the substances in order of increasing melting point. Okay, so with this one, the stronger the force, the higher the melting point. So for Monday, Wednesday, this is the extra credit video that's due on Friday. If you haven't seen it yet, you should do it. Or Saturday had their own extra credit video, so this one's yours. Okay, so when it came to this one, the best way to end up doing it is it's actually based on size. So dispersion forces, these are all nonpolar. When you just see carbons and hydrogens, nonpolar. It's always nonpolar. So you're gonna check size. So the bigger it is, the higher the boiling point, the melting point. Bigger is better when it comes to boiling point and melting point. So you're going off the one that's increasing in size. So in this case, D shows that CH4 is less than C2H4, which is less than C3H8. So D would be phosphorus pentachloride is a white solid that has a pungent and unpleasant odor. And it's used as a catalyst for certain organic reactions. Calculate the number of moles in 38.7 grams of phosphorus pentachloride. So the very first thing that we got to do is we're going from it was a really wordy problem that really just kind of in the end said that we were going to go from grams to moles was the entire idea of this one. So we have 3 conversions we can choose from. In this case, we're going to go use molar mass to go to grams to moles. So we have to calculate our molar mass for PCl5. So we got to find all of our values from the periodic table. So you have 1 phosphorus, 5 chlorines. So what I did is I just found the values from the periodic table. So phosphorus is right here. Chlorine is right next door. So we're going to record those values and then bring them down into our problem. And then we're going to figure out our molar mass, which you should have gotten about 208.22 grams. And that's equivalent to 1 mole of PCl5. So now the problem said to find moles of PCl5. Just kind of double check. Yep. So it's asking how many moles there are. So all we're going to do is we're going to take 38.7 and divide it by 208.22. And we should get the answer of B, which was 0.186 moles of PCl5. So that would be your answer in that case. Okay. So just how to go and get into moles. So just a one-step conversion. This is really wordy. A lot of times it's just background distractor information. What is the process in which a molecule undergoes a phase change from a liquid to a gas? Easy peasy, right? Vaporization, boiling, you could use either term. Both of them go from a liquid to a gas. What is the Q if 28.6 grams of water is heated from 22 degrees C to 78.3 degrees C? The specific heat of water is 4.184 joules per grams per Celsius. With this one, the whole idea is laying out the problem is crucial. So I write down all my values that I have so that way I'm not looking at a wordy mess every time you have a word problem. So the first thing is I put delta T in purple because usually that's kind of where you want to start is you want to calculate change in temperature, which is going to be final minus initial. So you have 78.3 degrees C, and you're going to minus that by 22 degrees C, and you'll get 56.3 degrees Celsius. Now we have every value that we need to plug into this problem. So we're going to be kind of taking all these pieces and plugging them into the MCAT equation. So what we'll have is Q is equal to 28.6 grams. Multiply that by 4.184 joules grams Celsius times 56.3 degrees C. All right, so once we multiply all those values together, let's see, you end up getting E, which I'm assuming is probably one of the kilojoule values. So with that, when you solve, you'll get the following number. So you're going to get 6,736.99 joules. And the thing is, you're going to see it doesn't match any of the choices, but energy can either be in joules or kilojoules or calories. So you kind of got to be aware of all where it can be. So when it comes to kilojoules, we simply just have to luckily just divide by 1,000. So 6.736 kilojoules is going to be how many kilojoules will be when we divide by 1,000. We round it to the correct sig figs, and that would be our correct answer, which in this case was E. Okay. Right. That's kind of the idea. Let's switch back to our other screen. How would you name the compound MgCl2? So with this question, if you find that you really need to use the blue naming sheet, then for ionic and covalent, those are pretty much the only type of molecules I ask you to name on the exam. There are no acids that you have to name. So there's no acid naming. It's either going to be ionic binary, ionic tertiary, meaning a polyatomic, or covalent. So just one of those three. I would really recommend you really try to master that naming because a lot of times chemical reaction questions are written with the names and not the formulas, which is really extra hard. And you also want to be able to read chemical bottles and labels in labs and, in hospitals and places of work. So it's always helpful. So with this one, right, whenever we name a ionic compound, we have a metal and a non-metal. Magnesium is our metal. It's our cation. It's named first. So we say magnesium. And being that's bound to the anion, chlorine, the ending changes to chloride. So it would be magnesium chloride would be the correct answer. With red, that's actually referring to covalent naming. So we use prefixes. So the di in that case is whenever it's covalent, meaning only nonmetals are used. So you have to identify, is it a metal or is it a nonmetal? When it comes to blue, for those that pick that one, that's if it's a transition metal. So if it was manganese, so Mn, then you would be maybe correct. But being that this one is Mg for magnesium, then you got to make sure that it has a predictable charge. It's 2+ charge. It's always the same charge. So a Roman numeral is not required. Specific heat of a substance is the amount of heat needed to do what? What is the definition of specific heat? All right. So with this one, specific heat, the units for specific heat are joules over gram per Celsius, meaning that the amount of energy, so joules, is needed to raise the temperature by 1 gram of that substance by 1 degree Celsius. So it's the actual definition of that particular thing. All right, when you guys try to name this one, I'm going to go grab a blue sheet, and I'm going to double check that question that was asked. All right, so trying to name this one. So the question was asked, what do you exactly need for naming? I mean, realistically, it's still pretty much almost the whole thing. The only thing that's not included is acids. So it's just that far left-hand side, or so the far right-hand side of the table. So covalent binary, diatomics, you still need to know diatomics. And then the ionic binary and ternary are all, just that whole left-hand side of the paper. So it's still almost everything in the end. Just because they're so commonplace in terms of chemistry, biology, and the health sciences, it is really important to be able to speak the language with it. So with this one, right, we would name the metal first, just like we did before. We would have aluminum as our name. And then the hard part is really remembering, do you need a Roman numeral or not? So it is aluminum sulfate. You only need a Roman numeral when it is not a predictable element. So in this case, aluminum has a same charge. It's a 3+ charge no matter what. So you do not need a Roman numeral to illustrate that charge. And usually it's only for the transition metals. I think aluminum is just right outside of that. So what is the formula for copper 1 sulfide? So copper 1 sulfide, the big thing with this one is what exactly do you do? So you have copper, right? And now the 1, just to kind of color code it, represents the charge of the molecule. So it's copper 1, right? So +1. Now the next thing is we have sulfur, and we want to look up what the charge is of that, which will be 2-. So it's in the second from the right column. So we can see sulfur is right under oxygen. So this is 2-, and you have 1- and 3-, right? So sulfur is right under that column. So when we swap drop it, what are we going to end up getting? You're going to see that you're going to have Cu, and you're going to have the number 2 next to it, and then sulfur next door. So Cu2S. We're going to trade those numbers on both sides. Okay. So we're going to swap drop. All right. What is the name of CrNO3? So, okay. Looks like most of you guys got this one. So chromium, this one's a transition metal. So it's not in our steps. So that means that we'll need a Roman numeral. So when you find in the periodic table, it's right in the middle of the transition metal area of the periodic table. So it would be chromium 3+. So just to kind of go through, how do you know it's 3+? How do you know it's not 2+ or something like that? Really the way to kind of go through this kind of problem is identifying what the charge is of the polyatomic or whatever's predictable. So being that this is our formula, the charge of nitrate is -1. So what does that mean is that being that you have 3 of them, so that means you have 3 times -1. So what does the charge of chromium need to be to balance 3-? Well, it needs to be 3+. It needs to be balanced on both sides. So being that chromium, being that it's a transition metal, does have variable charge, we need to show it in the name. So it needs to be chromium when you do it. And that's another reason why I say, like, memorize the polyatomics, because if you can get that, you can quickly see that, oh, nitrate, I know it's NO3, I know it's -1. It's like one less thing for you to look up. It saves you a lot of time when it comes to tests, and it's just less anxiety later, too. Or a molecule formed from N and Cl would be what? So how would N and Cl bond together? So for this problem, if you want to draw NCl3, we did it earlier, but in case you forgot, first thing you have to do is they are 2 nonmetals that are bound together. so that it's not going to swap drop charges. We need to write out the valence electrons. So we have nitrogen, which has 5 valence electrons. Then we have the chlorines, which each have 7 dots, so 7 valence electrons. So we're going to draw those first. And then once we draw all 7, we're going to connect them with a single bond. So we see that each one of these is now connected. And this would be your complete structure. You would need 3 chlorines in order to complete this particular one to satisfy its octet. That's how you do it. The strongest interactions between molecules of ammonia are what? What's the strongest interaction between molecules of ammonia? So you guys are, so a lot of you are right? It's hydrogen bonding. So how do you know, right? So you do see that there's lone pairs on NH3. So it definitely does dipole-dipole. But if you ever see an NH in a formula, or FH or OH, that's going to be hydrogen bonding, right? In this case, we do have that NH3 that's written in the structure. So that one's going to be, and it's going to be hydrogen bonding is what it can do. Carbon tetrachloride molecule, CCl4, has a what shape? So what is the molecular shape of carbon tetrachloride? So with this one, right, the whole thing with trying to get this one just to see it. So you guys got it correct, which is great. We're gonna have CCl3. So, or sorry, why did I say 3? CCl4. So we have C goes to a chlorine, 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 being that carbon can make 4 bonds. We'll see that it has 1, 2, 3, 4 groups that are all around it. All right, so being that we do have those 4 different groups, it's going to be 4 groups, no lone pairs, being that we have our central atom is carbon. So once again, we are going to have tetrahedral. The bond in Cl2 is a what? It's ionic, polar covalent, nonpolar, or no bond at all. So it's nonpolar. So how can you tell? So if you look up one, it's 2 nonmetals. So it cannot be ionic when it's 2 nonmetals. It needs to be a metal and a nonmetal to be ionic. In order to tell if it's polar or nonpolar, is that they both have the same electronegativity value. So being that they both have an electronegativity value, I believe, of 2.5. So if you take 2.5 minus 2.5, it equals 0, which is going to be, all right, choose the best Lewis structure for OCl2. So what is the best Lewis structure for OCl2? And if you go off bonding trends, it's a lot easier of a problem. So let me talk about the bonding trends briefly because I don't think I really mentioned them earlier. The big thing with bonding trends is that you kind of just go off how many valence electrons there are. So hydrogen can make 1 bond because it has 1 valence electron to share. The second column only has 2 electrons, so it can only share 2. Boron only has 3 valence electrons, so it can share 3. Carbon has 4, so it can share 4. Now, being that we follow the octet rule, nitrogen has 5, but it only is willing to share 3 because it only needs 3 more bonds to make an octet. So 3 plus 5 is 8. Then with oxygen, you need 2 more, and then fluorine, you need 1 more. So why is that so important is because you can see that oxygen will make 2 bonds on each side, and it's asking you what OCl's geometry is. Now, if we go back to like the question, right? So seeing that we can only make 2 bonds from, we'll see that the O on the green example only has single bonds on each side. It's the only one that only has 2 bonds. All the rest either have 3 or 4 bonds all around it. So it's the only one that's possible in this case to form that bond. Okay. The temperature of a 159 gram piece of an unknown metal increased by 43.4 degrees Celsius when 6.88 kilojoules of heat is added. Determine the specific heat. So we're not doing joules this time in terms of energy. We're going and rearranging our equation to get C. Let's take a look at how to do this one, just because clearly you probably need more time with this one, but you know, if you were on test, hopefully you have a few minutes to do it. We're going to use the MCAT equation. So the first thing what we have to do is we're looking for C. So it's the only thing we do. So I listed out all the values and you see C is the one thing missing. So how do we get C by itself is, well, we got to rearrange our equation. So we're going to divide by m and delta T by both sides. That way it gets rid of m, gets rid of delta T on the left, on the right. And our new formula is going to be Q divided by m delta T is equal to C. So now when we have that, we want to make sure all of our units are the right thing. The one thing is, you might notice, if you remember, specific heat is joules over grams per Celsius. So the heat is actually needs to get converted to joules. So you need to multiply that by 1,000 before you can use it. So we'll do that first, and then we can then plug it into our equation. So 6,880 divided by 159 grams times 43.4 degrees C. And this will equal our C value. So when we end up putting that in, what we're going to end up getting is 0.997 joules per grams per Celsius. And usually for most metals, it's typically below usually below 1 joule per gram per Celsius for the most part. Usually being that's a lot easier to heat up a metal compared to something like water as well. So you could kind of take an educated guess and probably go with like the red, blue, or green answer in this one, if you were to go through it. Okay. So this was the last problem in the review. So let's see who ended up winning. And I think it was Catherine. I think she was pretty far ahead. So go through our podium, and hopefully, thank you guys for listening. Good job, everybody, for sticking through it. I know this is a really long thing to kind of sit through all the questions and everything like that. And I hope that it helped a little bit. So kind of going through the kind of questions you could see, right? Just to go over some of those basic concepts, and I try to throw in a little bit more intermolecular forces ones, being that I know a lot of people are struggling with that. Keep in mind, if you need help, you can go to ETC throughout the week. There's also GRASP on Friday, which I really recommend. Can't recommend it enough, being that I'm usually there for, I don't know, anywhere from 2 to 4 hours, depending on how many questions you guys have. So I'm usually there starting at 10, but the doors to GRASP open as early as 8. So if you want to get there a little early and get help from the other faculty there, you have that option too. I did record it. So I recorded it separately from Zoom. So everything is being recorded through a different program. All right. Well, if you guys need help, reach out to me on Discord, email me, put stuff in the forum, or just direct message me, whatever's easier. Come to office hours, and I hope that I can help you as much as I possibly can. Okay, everybody, that's the end of the review session. Thank you so much for listening. I really appreciate you spending the time and hopefully making it to the end. It's a lot of work making it to the very end of the review session. On the actual review, there will be some bonus problems, so make sure you do them on that test. They might be involving, if you do watch all the way to the end, they might be involving 7 of something that you do commonly. I have you list out using different acronyms to help list out 7 of something. So that is a hint towards one of the bonus questions. So it's a reward for watching this long. All right. Thank you all so much. I hope you all have a wonderful day, and I will see you all later. Bye now.